Our universe is a strange place, with underlying rules we're only just beginning to understand. But could the strangest thing of all about our universe be that we are able to live here to observe it in the first place? Knowledge is power, and the kind that earns interest on your investment. The more you know about any situation, the easier it is to learn more about it because you know the right questions to ask, and every new answer or test result yields more information. Much like a jigsaw puzzle, each piece gets easier as you go, since there are less pieces to try to fit to any remaining empty spots, and you've grown more familiar with that image and the subtle differences in texture or color that help you see which pieces fit with part of the wider image. The universe as a whole is quite the jigsaw puzzle, and we can only see it by what's visible here on Earth, a tiny grain of sand against the wider galaxy, which itself is a tiny grain next to the wider cosmos. It would be akin to studying all the Earth from inside just one room of a house, with just one window that's all fogged up and scratched. This means we've often had to work from a standpoint of very little information about the universe and very little way to gather more. One of our core assumptions in all of modern astronomy and cosmology is the universe is more or less the same everywhere, that the speed of light was the same a billion years ago as now, that it is the same here as in the Andromeda Galaxy or halfway across the known universe. That matter in other stars and planets is made of the same elements as on Earth, and that each of those elements are made of the same basic protons and neutrons, or up and down quarks, that there are no other places with different rules or constants. We can't go to any of these places to check this, so it is merely an assumption. There are a number of physical constants that we know of, things like the strength of gravity, the speed of light, Planck's constant from quantum mechanics, and more. When we contemplate even tiny changes to one of those, models tend to show not only that life as we know it couldn't exist, but that no life would be possible at all, that there's a very narrow band of ranges in which life is possible, and that we seem to be finely tuned into those bands in this universe. We'll be discussing the pros and cons and strengths and weaknesses of this concept today, along with its implications if true, but let's return to that assumption of a moment ago. We assume that the universe works elsewhere much like here because we can't go and test it out, and our observations at a distance tend to reflect a certain sameness to reality that we wouldn't really expect if the rules were different for each star system or galaxy. So it's not a wild guess, but it is an example of being forced to draw conclusions off of virtually no information and with no expectation of getting much more in the near future. Working from a standpoint of being able to have lots of information on a topic and acquiring more quickly is always our preferred state. But when you have virtually nothing and no clear way to get more anytime soon, you have to choose if you want to speculate on a matter or not. If you do, we have two general approaches to doing this. One is the Copernican or mediocrity principle. It's where when we encounter something new, we assume it is probably relatively normal and mediocre. If I reach into a bag full of marbles and pull out one half an inch wide and red, I assume that it is likely there are more of those marbles that are red or half an inch wide. Even if I pull out 1,000 of them and each is half an inch wide and red, I still don't know that the ones remaining are that size, and color too, but it seems pretty likely. And each additional one makes it more likely. Back when I only drew one, that conclusion would be made with a lot less confidence. Each new data point adds more confidence, unless I draw something else of course, like a blue marble half an inch wide, in which case my confidence in all marbles being half an inch rises. But I now have a sample of blue and red, and each draw will raise my confidence on what the ratio of blue to red is, or blue, red, and green if I pull a green one next. And that is our basic approach to science, and relies on the idea that I can keep grabbing marbles fairly easily. Note that it doesn't tell us why those marbles are all half an inch. And we might also find that the bag is full of bigger marbles, but the hole they are coming through is only half an inch wide, so they won't fit and we don't see them. Our alternative approach is called the anthropic principle, which is where we look at the situation and ask if the results or info we are getting might be influenced by us as an observer. Say if I had a scoop that couldn't grab marbles bigger than half an inch, and from which those smaller than that would fall out. As another simple explanation from our previous example, imagine someone had a bag each of red marbles, blue marbles, and green marbles, and then left each of those bags in a separate room with a door colored the same as those marbles in it. If red was my favorite color, I might have walked into that room and thus found that bag of red marbles. And as common as the mediocrity principle is in science and even daily reasoning, the anthropic principle is equally so. We tend to assume our decisions are impacting the items and events we are encountering. We know that the reason we bumped into someone is often related to those. If I go to a comic book convention, I shouldn't be surprised to see someone dressed up as a comic book hero. If I walk into a store and someone comes up and greets me, I am right to assume it's probably because they are a salesman or the store greeter and not a representative slice of normal human interaction. An alien arriving on Earth in human guise might not realize this about any of those situations. And again, this is very focused on the idea of what to do if you have little data and get more of it, since that's not the default norm. If I try to explain either the mediocrity or anthropic principles to someone, it is normal for them to suggest simply getting more information and to immediately follow that with several entirely functional means of doing just that. So for the purpose of discussing the concept, we have 3 typical thought experiments or scenarios that tend to get used precisely because it's basically impossible or very impractical to come up with more information on them. One of these is the simulation hypothesis, the idea that we might live in a fake world, and one so good there was no obvious way to tell. So we speculate on the probability that some reality in which computers are powerful enough might have several of them running simulated realities, which are then more common than the real one, and thus it's more likely we would be in one of those fakes. The next one is the doomsday argument, which reasons that there's a finite number of humans who will ever live, and that statistically we would expect to be a mediocre example of one, and thus for our birth order, when we were born in relation to that first and last human, should be fairly near the middle, not the first or last percent. And since there's only been 100 billion people ever to live, if we were in the last 1% to be born, then we're done inside this century. While even if we were that first 1%, only 10 trillion people will ever live, and at current numbers, we would go through around 10 billion a century and be done in about 100,000 more years. An eye blink compared to the age of Earth or our universe, and you can see the Doomsday Argument episode for more discussion on how this math and reasoning works. The fine-tuned universe says the odds of us living in a universe with such a perfect arrangement of physical constants is very low, so either we lucked out and there are tons of other dead universes out there, or there are not, and our improbability is a side of those constants having to be that way, either from some unknown other principle or from someone of immense ability making them that way and making the universe itself. In short, to discuss the basic philosophy of drawing conclusions from limited data, we use examples where it's very hard to get that data and also very mentally interesting examples. For a lot of folks, they boil down to the simulation hypothesis. Is our existence real? The doomsday argument. Is our existence soon going to end? And the fine-tuned universe. Is there a creator God? I will now go ahead and give you the answer to all of those, from the reasoning of the anthropic and mediocrity principles. The simulation hypothesis. Is our existence real? Answer. Possibly. There is as yet insufficient data for a meaningful answer. The doomsday argument. Is our existence soon going to end? Answer. Possibly. There is as yet insufficient data for a meaningful answer. And the fine-tuned universe. Is there a creator God? Answer. Possibly. There is as yet insufficient data for a meaningful answer. Welcome to Science and Futurism with Isaac Arthur, where we're not afraid to ask the big questions about life, the universe, and everything, and where we will also not be afraid to admit we have no idea about the answers. For alerts when more episodes come out, don't forget to hit the subscribe button or those like and join buttons to support the show, and don't forget to grab a drink and a snack either, as in spite of not being able to give any definitive answers, there is a lot to talk about, so we will be here for a bit. To carry on that key point though, as important a question as it is, at no point in this episode are we going to prove or disprove God, or seek to show the universe as is could only plausibly have arisen by artifice, or that there must be a multiverse to explain the apparent huge improbabilities of our universe. Emphasis on apparent too, because we don't know that other values for physical constants are possible outside of math. We don't know why they are what they are and can't assume that they are thus random, and more importantly, we don't have one iota of proof that this universe is or is not alone, as opposed to being one of near infinite arrangements or one a layer below some other greater reality and engineered by some other mind or minds. We'll discuss all that today and the reasoning many offer for it, and there's a lot of them, but to get the two biggest ones for and against out of the way, the idea that this shows the universe to be created by some outside agency takes the simple reasoning that the constants of the universe seem to need to fall into much too slim a range of possibilities, and it is an insanely improbable figure too. We'll get to that in a bit. And thus the odds of life being possible in this universe are way worse than getting struck by lightning and a meteor while winning the lottery all at the same time. This is the basic reasoning of why those constants would point to an artificial universe. It doesn't directly speak to whether or not that's some smart alien computer programmers in a higher layer of reality or a creator deity, and if the latter, which particular creator deity it would be. The other line of reasoning says that yes, it seems improbable beyond belief, but even if it is 1 in a quintillion jillion odds of having a universe with the right constants for life, that just means you have to assume there's a quintillion jillion other universes out there, virtually all of which are dead. Only in a universe where life exists can they grow sentient and start asking questions like why life exists and how unlikely it is. All those dead universes simply don't have anyone able to look around and be unimpressed with the entirely high odds that the universe they are in is lifeless. As an example of that, you were born of the trillions of sperm and millions of eggs your father and mother had in their lifetime, that exact combination being in the quintillions, and yet you don't really think much on the improbability of your own existence and ability to note it. And that's logical enough reasoning too, but is also the source of a lot of the support and objections for the concept of multiverses, because there's absolutely no evidence they exist, or that they do not exist, so simply assuming they do exist to explain away the fine-tuned universe reasoning tends to seem like a bit of a cop-out. Incidentally, these are not the regular multiverses you see in way too many sci-fi films and franchises these days. Alternate timelines that honestly seem more like lazy writing or cheap excuses for retconning a setting than good storytelling, with some notable exceptions. Those multiverses are alternate timelines. Someone did or didn't stop for coffee that morning, or did or did not fire nukes at an enemy. They're not different in the sense of coffee or nukes not functioning because chemistry or atomic physics isn't operating the same. Some would also make the case that altering a given physical constant would have no effect, as an extension of the reasoning that if everything, including you, were twice as big, you would not notice a difference. Or if time ran half as fast, you couldn't tell since it runs that way for everyone, and that only altering the dimensionless quantities, like the fine structural constant, would matter. More on that later, but it just shrinks our example cases. For my part, I think a lot of folks jump so quickly on bandwagon A or B that they ignore C, which is simply that those physical constants may not be able to have any random value, but are limited to some range or discrete values, such as we often find occurs as emergent properties of one system sit on top of another. That obviously implies some other foundational system or reality those constants would be getting determined from, but both A and B, God did it, or random immensity the multiverse did it, also assume that additional layer of reality. There is no evidence of such a layer, though again, no evidence against it either, and here at least we can back reason a bit from the way we do see discrete layers in the scale of the universe. The boundaries between the nuclear and atomic and molecular, then to the macroscopic, and then to the scales where gravity grows increasingly dominant over other forces, and then as it weakens against dark energy, all show very different looks. It's not just another box inside another box, or another identical but smaller doll, or an arbitrary line between layers. Each layer has a very distinct appearance and behavior, and often seemingly arbitrary things on a layer are not, and determined by the rules of the layer below. As an example, a water molecule is a very common thing in this universe, 2 hydrogen, the most common element, and 1 oxygen, the third most common element. It's not really surprising that hydrogen and helium are common. They are simple elements of 1 or 2 protons and 0 to 4 neutrons. but oxygen is typically 8 protons and 8 neutrons, and sometimes can be 9 or 10 neutrons instead and be stable. Indeed, it can have other numbers of neutrons too, but be less stable, lasting just seconds or fractions of seconds. Why are these 3 isotopes stable and others not? Why are lithium, beryllium, boron, carbon, and nitrogen less common than oxygen, for all they have fewer protons and should seem easier to assemble? And when we get to that water molecule, 2 hydrogen clutching onto that one bigger oxygen atom, why aren't they on the exact opposite side of the oxygen? Which would seem intuitively correct. Instead, they are separated by 104.5 degrees, not 90 or 180. Someone might ask if there was a universe where they were at 104 or 105, not 104.5 or 104.6, or 179 or 179.1. And this was quite a mystery and hardly unique to water. Ammonia, another supercommon molecule in the universe with 1 nitrogen and 3 hydrogen, has a 107-degree bond angle. But there is a reason, and it is an emergent property of that layer of reality below, the atomic realm of electrons around a nuclei where quantum effects like spin and uncertainty vie with electromagnetism, and we get an effective dual domain of inner electrons and outer valence electrons. Were those physical constants, Coulomb's constant or the speed of light or Planck's constant, different, then that angle would be too. But there's not going to be a universe where those constants are what they are now and that angle is different. Its value is not arbitrary or weird at all, it simply looks that way to us without that deeper knowledge we've since gained. So too, our macroscopic universe, our day-to-day existence, is decidedly mechanistic, where the same action on the same item produces the same result every time. But this is not true of the quantum realm it is built on, where things happen with a statistical likelihood instead. But if you flip a billion coins for every decision, a billion quantum-level atoms for even the tiniest grain of dust, your probability fits into a very tight bell curve that from a distance, seen through a microscope from our realm, so to speak, appears a perfectly flat and straight line, not a bell curve. Everything in our scale obeys that quantum realm, but there are emergent properties like that bent water molecule that much more simply and intuitively explain the system at our level. The same applies to how planets and stars work. Fusion in stars only occurs because of quantum effects, for instance, and yet cosmology has a separate and basically complete rule system that you can mostly understand without knowing of our scale or the atomic and their local rules. We obviously do not have a very good grasp on what occurs at the subatomic scale, thus all the expensive supercolliders, and the scale below that is even more mysterious. So is the extragalactic scale, where dark energy dominates behavior. And if the universe goes far beyond the observable parts visible in spite of Hubble shift, it may show other emergent properties at that yet larger scale. We should not simply assume those physical constants can be any random value then, as they may be emergent properties of some deeper layer of reality. Now, does this mean there isn't a vast number of other universes with different physical constant values? Or that there is not a creator god who set them for this singular universe? No, that's not a certain conclusion either. It could be either of those 3 or something else entirely, or even some mix. Again, there is as yet insufficient data for a meaningful answer. Scientifically anyway. The error here is a tendency to treat those as binary options, that the apparent narrow window for life to exist with those physical constants only can imply either God did it, or there's so many alternate realities that even this insanely large improbability has to be true somewhere, and we could only exist to observe this improbability of our own existence if we had won that lottery. You can also make the case that assuming those constants have to have some non-arbitrary value just kicks that can down the road again, pushing it onto a lower layer of reality where other effects dominate and which might have their own arbitrary seeming constants, which may or may not have been set by some divine power or result from some insanely improbable but random arrangement of values for those constants. And that may be, but I still want to know why a water molecule is bent, and why light signals or gravity take a certain amount of time to travel. I don't feel like we kicked the can down the road to learn the nature of atomic forces or the speed of light. I also don't like the musings that assert that there's always some new puzzle for every one we solve, like a Hydra spotting 2 new heads, because it implies we're spinning our wheels in the mud and not getting anywhere, in some futile eternal quest for knowledge, because none of these new layers is identical. It's also assuming there's an infinite number of them, which is just a guess, like a person assuming there's an infinite number of trees because they are in a forest and can only see a few hundred feet around them and see trees, and when they walk a while, still see only trees. It may be infinite, but throwing their hands up after looking for a few minutes and assuming that's the case isn't really justified. But most importantly, it's implying the quest is futile because of the possible infinity, which, even if infinite, would only be true if we weren't gaining at each step. Science has hardly been a zero-sum game of spinning our wheels in the mud. Just check with your ancestors a few centuries back who spent all their time walking barefoot in mud, or their ancestors a few millennia back who didn't even have a wheel to spin, and tell me that's a zero-sum game. I do love Fine-Tuned Universe, the Doomsday Argument, and Simulation Hypothesis for conceptual discussion. We've done episodes on the other two as well, and they are good thought experiments, but they are so philosophically charged that folks often tend to gravitate to the answer they would like to be true, rather than understand that these three problems specifically exist because they cannot be properly answered. At the moment, anyway. We could come up with tons of hypotheticals that would illustrate the difficulty of picking between the anthropic and mediocrity principles when you have little available evidence, but they are less interesting, as would just be examples like our earlier example with marbles, less philosophically fascinating, but also less likely to make someone lose their marbles based on the apparent options for conclusions. Only the last few folks around for Doomsday, be they now or some final last planet at the end of time, are going to know how many people ever lived and where their birth order number stood in that count. Your actual status in it in no way dictates the causes and effects that would end humanity. It's just a probabilistic argument that's neat for sounding grim and highlights the strengths and weaknesses of that approach to problem solving. As for simulation hypothesis, if it's a good simulation, you can never find out you're in one unless the creators of it choose to let you know, or until you reach the edge of what they cared about trying to make seem real, as we looked at in Hacking the Simulation. As I often say on the topic, even before computers, it was common to ask if everything around us was real or not, but I tend to feel the better questions are if it actually matters and what do we mean by real. Just because you're under a higher layer of reality made by, say, God, or sitting above some more foundational layer of reality doesn't mean you're not still part of reality. We could just as easily be in a vast multiverse with tons of varying physical constants that was created by God or a programmer, and we could live in a natural universe that was singular, no multiverses of changing physical constants, and they just happen to not have arbitrary values. And again, the alternate timeline multiverses most of us know from fiction all have the same physical constants, just different events unfolding. Speaking of those many possible values though, why is it that we talk about a really narrow window for life, and can we really make that assertion that it's any life? The short answer on the latter is no, and is where Boltzman brains pop up, but they are also hugely unlikely, and I think it's time to talk about those numbers and how this ties into the Fermi paradox, the big question of where all the aliens are in this enormous and ancient universe. Why would the speed of light, being half its speed or twice its speed, make life impossible? Why would the strength of gravity rising do the same? Why is the number of dimensions limited? Let's talk gravity and dimensions real quick. You will have heard many times about 2D universes and folks going on about multiple higher dimensions that did not expand as an idea under string theory. I will note that there is absolutely no proof of string theory or higher dimensions, though they also have a compelling case, much like multiverses. Nobody was just feeling bored one day and decided to make things more complicated sounding. The assumption is that those other physical dimensions did not expand when the Big Bang occurred, which might sound weird, but keep in mind the weird thing is not them not expanding, is that the other three did expand. The Big Bang is weird, and seemingly broke a lot of rules like conservation of energy for instance. Until we know why that happened, worrying about why the others did not happen is a bit secondary, assuming they even exist. Gravity and electromagnetism both fall off in strength over distance with the inverse square of distance. Twice as far away, a quarter the strength. Thrice as far, a ninth. 10 times as far, a hundredth. This is because they are expanding out omnidirectional in 3 dimensions that seem to stretch out forever in every direction, and the surface they expand on is two-dimensional and rises with the square of the radius. If we lived in a two-dimensional universe, that force would fall off inversely with distance 10 times further away, a tenth the strength. If we lived in one where it was infinite in 2 dimensions, but in a third only expanded out, say, 1 light year, before wrapping back on itself or just ending, a thin sheet like paper, then it would act like it does here at the smaller scale. And once light or gravity had expanded to that light year scale, suddenly start acting differently, perhaps simply being inverse. If we had all 3 dimensions but one or more of them was expanding constantly, things like gravity and light start falling off faster at bigger distances because they are still weakening inverse square, but now they are also stretching and getting stretched faster the further they go. That's the concept of Hubble expansion and dark energy. Double the speed of light, which is also the speed of gravity, and you should be able to see, or signal, twice as far before the cosmological event horizon began to limit new interactions between sections of the universe. And gravity would similarly have a long reach. Right now, it's not just that I can't send a beam of light to a destination about 14 billion light years away because the universe is expanding faster than light at that distance, you also can't have any gravity affect you that's originating now from that far away. So if the universe is much, much bigger than that, we would assume at that larger scale that gravity plays little role, much as atomic forces are not important to planetary and stellar motion, mostly. That's one of the problems with why a very large universe can't just collapse back in on itself one day. In Fermi paradox context, it's also why we don't really speculate on the frequency of aliens beyond less than about one civilization a few billion light-year radius. Out beyond this, we wouldn't even know if one arose, and their colonies and ours would never reach each other to meet and say hello, even if expanding at relativistic speeds. The universe may go on for trillions of light years or quadrillions or more, and be home to millions of civilizations who will never be able to signal each other because they are less common than 1 per Hubble volume. Things shift in 4 physical dimensions though. Now if I have a set amount of substance in space, say a big nebula with about a star's worth of material waiting to form, those individuals are now effectively way less densely packed. A 10 by 10 grid of paper with 2 particles in it, 1 by 1, has 2 particles per 100 spots. That's a density, and they're bouncing around moving at some speed and can occasionally collide, something they do a lot less if moving slower or if that grid was instead 100 by 100, so they occupy just 2 of 10,000 spots at a time. Go to 3 dimensions and that density of a pair of 1 by 1 by 1 particles in a 10 by 10 by 10 grid is already just 2 in 1,000. Bump it to 100 wide and now it's 2 in a million. Interactions occur more rarely, things are less likely to clump. Go to 4 dimensions, and your grid 10 wide has a density of 1 in 10,000 and 100 wide by 1 in 100 million. 5 dimensions, and it goes to 1 in 100,000 and 1 in 10 billion respectively when expanded. This is the first point of difficulty with higher dimensional life. Life requires particles to interact. And if it's in a universe that's spreading like ours, it rapidly spreads too thin in a higher dimensional universe. And gravity isn't doing a great job drawing things together, because it works through virtual particles interacting with things too, gravitons, and is now an inverse cube force, not inverse square, so is much weaker at a distance. You probably wouldn't get much planet or star formation, and if you did, those orbits are very unstable. A perfectly circular orbit, or its 4D equivalent, is very unlikely to occur naturally, and the less circular it is, the less stable it is, because when it's closer to the primary body it orbits, the strength exerted on it is higher, and when further, it is less. And the more eccentric, the more unstable that orbit. This is even worse when gravity is rising in strength or weakening in strength much quicker with distance. Our models indicate no stable orbits are possible in higher dimensions, and gravity isn't the only type of orbit you can have. It applies to electromagnetism too, even if the planetary model of atoms is all wrong. And so it gets really dubious if you could even have stable interactions of matter in higher dimensions. Needless to say, there's a lot we don't know and limits to our modeling without any ability to experimentally check them. Gravity might be stronger too in other universes, and indeed it is weirdly weak compared to the other 3 forces that are at least within a few orders of magnitude of each other. Gravity is strictly attractive and trillions of times weaker than even the weakest of the other 3 forces. so it's not hard to imagine it being stronger. There's an excellent book called Raft by Stephen Baxter, which looks at a universe where gravity is 1 billion times stronger than here, still making it trillions upon trillions of times weaker than other forces, and he examines what that universe might be like. Baxter is a mathematician and engineer and focuses on writing hard sci-fi, and he's great with the technical details. We get no planets, just burned out husks of microstars a mile wide with semi-livable high gravity and new concepts like gravitic chemistry. And it's right up there with Robert Forward's Dragon's Egg and Abbott's Flatland for intriguing speculation about weird ways life might exist in altered realities. I think that's an important bit to note, because we can't really say definitely no to life in other places like those, though you can pick apart any of those 3 books for critical flaws that would seem to make life impossible there. A key point for consideration in a moment, though, is the idea that it might not make life impossible, but simply less likely. When it comes to discussion on fine-tuned universes, you will hear a lot of numbers thrown around. 1 in 10 to the 120 seems to pop up a lot. 10 to the 120 is an almost obscenely high number, trillions upon trillions upon trillions of times larger than the number of individual atoms in this universe. But these are typically arbitrary numbers. I could say that life could only exist if the speed of light was between 100 and 100 million meters per second. Its current listed value is 299.8 million meters per second, incidentally. And basically that's one whole order of magnitude, the range of 10 to the 8 to 10 to the 9 meters per second. So we could then say any of those other bands of the same width might exist elsewhere, that if we contemplated possible light speed bands up to a quadrillion meters per second, 10 to the 15, that there would be 1 million such bands, in which life was only possible in just one, and thus only 1 in 1 million universes had a speed of light in which life could exist. That is an entirely arbitrary selection. You could have universes where the speed of light was 1 meter per second, or 1 nanometer per eon, and that top could go up a quintillion or a septillion or all the way to infinity, or all the way down to the infinitesimal. The same is true of any of those constants. The fine structure or Summerfield constant, the dimensionless one, is 1 to the 137, so we could imagine having any other value, say 1 in 136, or 1 in 138, or 1/2, or maybe 42. Or it could have a non-integer value, and indeed our current measurement of it is 1 in 137.035999084, and it probably has many more digits. It is the gap in the fine structure of the spectral lines of the hydrogen atom, incidentally, and is calculated using 4 other physical constants: the square of the elementary charge divided by twice the product of Planck's constant, the speed of light, and the electric constant. And that is either Planck's constant or Planck's reduced constant, which is the former divided by 2 pi, and we can also hypothesize about a universe where pi has a different value too. As I mentioned earlier, in a universe where everything is twice as big, or time moves half as fast, you can argue nothing is different, and for that reason, more or less, some folks discussing this topic feel that it's only changes in that constant that would matter, as a universe where those other 4 were all scaled up, but divided to the same fine structural constant might be the same. It's not the only one of note either. We do not know why protons are 1836 times more massive than an electron and have the same charge, or why quarks come in 1/3 and 2/3 charges, but proton to electron mass or charge are dimensionless ratios. So is the coupling constant of the strong nuclear force. We don't know why we have 6 types of quark and only 2 seem to show up in detectable matter, or why we have 6 leptons, of which the electron is 1. The cosmological constant is another dimensionless constant, and around 10 to the negative 122. And there's plenty more, and we could imagine any number of values for them. We could also imagine a plethora of multiverses with those different values too, in which at least some life is possible. We can also imagine life that didn't arise by something very basic and barely alive but able to reproduce from a pattern, and thus able to mutate and produce mutant copies and avalanche into a process of evolution, possibly eventually producing something like you or I, smart enough to ask why we exist and how improbable that may be. But a life form might have started partway up that ladder, not the simplest random object possible, but maybe somewhere around step 100, a slightly more complex proto-amoeba, and that might be 1,000,000,000 times less likely to happen, and thus still happen 1,000 times in a universe where 1,000,000,000,000 planets got life started. Same in a universe where the simplest possible self-replicating life was far more complex and less likely to happen, from different physical constants, it should not be 0. This is where the thought experiment of the Boltzman brain comes up, which is a randomly assembled and stable human equivalent brain. In practice, there are a near infinite, though not infinite, number of simpler steps that might assemble and then be able to grow bigger by non-random means, same as there are far more scenarios where the random brain is without any sensory organs or means of life support. Nonetheless, there is a finite probability of a full assembled thinking brain coming to existence somewhere, most of which would presumably be going crazy in their own hallucinations from a lack of eyes and ears or starving to death. You or I might be such a crazed mind hallucinating this universe, and there would be some that would be vastly smarter than a human. Indeed, you should have some universes where from the moment it came into being, that universe was one single immense and terrifying intelligent megamind, and that might be a much bigger universe than our own. Indeed, our own might be infinite. The question is invariably how likely such minds are to arise compared to evolution, and for our universe it is staggeringly low. Even if we don't really know the odds on that first life form arising here or the evolution that followed, we can show it is way lower than a Boltzman brain at least. But we need to keep in mind that when we get into multiverse thinking, staggeringly improbable things start happening a lot, and that in universes with other physical constants, this Boltzman brain may be more likely to assemble than life by evolution, especially the in-between state where what assembled is something like a small computer with the ability to self-replicate and grow itself, akin to the dreaded technological singularity scenarios. It might not need to be much more improbable than a single cell coming together, or in fact a good deal less. And you can build a switch out of pretty much anything, even a black hole if it came to it, which should exist in any place with greater gravity than ours. Where you can have one switch, you can't have two, albeit less likely, and 3, albeit even less likely, and 1,000,000,000 all arranged in good working order, albeit insanely less likely. Which might be apt since again, odds favor any full brain coming to existence on its own, lacking useful sensory organs, and rapidly going nuts inside its eternal emptiness, surrounded and aware of nothing but itself and its own mad hallucinations. And if you've ever felt that might describe your own existence, good news! The same reasoning that tells us we're somewhere between 33 to 55% likely to be living in a simulation says the odds that you're a mad Boltzman brain dwelling in your own fever dreams is pretty decent. Anyway, a simple life form, once begun, does not necessarily spread by dividing itself into countless other tiny life forms who slowly evolve to multicellularity billions of years later. It might go multicellular from the outset. Emphasis on might, because it might be staggeringly unlikely compared to how it happened on Earth, or not. I don't think anyone's modeled it successfully, but all it has to be in the context of infinity is some number smaller than infinity, and it will happen. And there are a lot of numbers smaller than infinity. Short form, even if there are tons of dead universes where no scenario like a planet Earth with life evolving powered by sunlight was possible, there may be way more of them than universes like our own, so that Boltzman brains, however improbable even in those universes, still outnumber examples of life in universes like our own. And this all matters to the Fermi paradox if we are imagining other universes do exist, and that interaction between them is in some way possible, since you do then need to consider some Boltzman brain emerging in such a multiverse and coming here to visit or settle, or even our probably not quite infinite but insanely huge universe-scale Boltzman brain that might find creating subverses a very easy thing to do, either simulated on its own immense brain or torn into creation by big bangs generated by its vastly superior knowledge of science. Definitely a more extreme take on the usual problem of computers all the way up and totals all the way down. As I said from the outset, multiverses are usually not a good answer to philosophical or theological problems. They just tend to cause more of the same issues, which would stand to reason since they represent so many more universes to cause problems, and even more if they not only existed, but were able to interact in any fashion to allow travel or communication between them. but they still cause us problems with the Fermi paradox even for this universe all by itself. Let us return to the idea that life might be possible almost anywhere, but in most places is very improbable, and in fewer places a little less improbable, and in yet fewer modestly likely. If we assume most universes are dead, or only the realm of a Boltzman brain perhaps, then there should be some more where life is unlikely but just possible enough that one single example would arise in an entire galactic supercluster in a billion-year period. There should be more universes where this was even less likely, 1 in 10 billion, or only in a region even greater. And there should be fewer universes where life was more likely to arise, say once in a million years or once in a galaxy. And fewer yet where it was so common it arose on a million planets in one galaxy, the typical assumption in most science fiction and space opera. And even fewer where life arose from inanimate material on its own so often that very nearly every rock had it and many had it happen independently repeatedly. The mechanisms for life and evolution are rather complex and tricky. Conditions in a universe are either friendly to life or not, and might be friendly on Earth but not Pluto or in the middle of a star, but the basic reasoning and math still works. If most universes have bad constants for life to emerge, there should be more of them that have barely viable constants than super friendly ones. Thus there should be way more universes where life arose a few times than a lot, relatively speaking, and thus we are more likely to be in one of those harsher but barely viable universes than one where life could emerge everywhere easily on its own. Such being the case, if we do live in a near infinity of universes, most of them dead, we may be lucky enough to live in one that isn't, but we probably weren't lucky enough to live in one where life arises abundantly. Though that's not necessarily something to consider as bad luck, given that it means we have a lot more space around us to grow into without running into alien competition, or extermination. In any event, that's the fine-tuned universe concept and the anthropic principle, or cosmological anthropic principle as it's sometimes called in this context, and its general pros and cons, complications, ponderings, and Fermi paradox implications. Definitely one of the more fascinating and existentially engaging lines of reasoning about our universe and place in it, or the wider cosmos, though again not one that permits me solid conclusions to be drawn, if any. But great for musing and discussion. Let me know what you think in the comments on the episode. Looking at the wider universe today in its unfathomable enormity sure can emphasize what a tiny pale blue dot we live on ourselves. As we journey out to explore the stars, it's easy to forget how much of our own world is still unexplored and full of surprises. Unfortunately, we're often losing species and ecosystems as fast as we find them. If you'd like to do something to help, let me introduce you to Planet Wild, your chance to make a real difference for our planet from the comfort of your home. Every month, Planet Wild teams up with a new conservation partner to save endangered species, clean oceans, or restore forests worldwide. Think of Planet Wild as crowdfunding for nature, connecting your contributions to impactful environmental projects. Planet Wild is for you if you prefer immediate action instead of waiting for others. Make a difference, help preserve our pale blue dot, and check the link in the description. And if you want to check out their work, watch their latest mission video in my description box where they're raising baby sharks and releasing them back into the wild. Usually sharks cause fear, but now they're the ones being in danger. And it's all community funded. You can support them big or small, whatever feels right to you. The basic membership is just the price of a couple cups of coffee a month. If you'd like to try them out, the first 150 people who join through the link in the description or use the code ISAAC7 later will enjoy the first month of a Planet Wild membership paid for by me personally. And the best part, you will already make an impact through that and see the results at the latest 30 days after. If you don't feel like supporting Planet Wild anymore, you can cancel anytime. No questions asked. As a quick side note, I recently had the pleasure of co-hosting This Week in Space with Rod Pyle, where we got to interview Evan Jensen from Icon Build, a 3D house printing company, to discuss their Project Olympus for printing buildings on the moon. And the next episode we had Jason Rhodes and Alina Kiesling from NASA JPL to talk about the Euclid and Roman missions and new data on dark matter and energy. Those were great conversations, and I'll be back on again in early August. Speaking of August, we'll be returning to the topic of the Fermi paradox on August 8th to consider how migration to the galactic core or rim or other universes might explain the Great Silence. But we still have a few episodes before then, starting with a look at self-repairing machines next week. Then we'll journey to the moon to contemplate mobile mining platforms and life as a lunar mineral prospector or nomadic miner on the moon. Then we'll start August off by joining Colonial Governor Maxwell Augustine and the Olympic fleet bound for the planet of New Actium, as we see what it would be like to be the governor of a generation ship and a fledgling colony. If you'd like to get alerts when those and other episodes come out, make sure to hit the like, subscribe, and notification buttons. You can also help support the show by becoming a member here on YouTube or Patreon, or check out other ways to help at isaacarthur.net. You can also catch all of SFIA's episodes early and ad-free on our streaming service, Nebula, along with hours of bonus content like Planetary Archives and Stasis Vaults at go.nebula.tv/isaacarthur. As always, thanks for watching and have a great week.